interactions. Or I was going to tell you about how string theory was discovered by accident, because people were looking for a theory of strongly interacting particles, and at the time they saw this large number of particles satisfying a relation of this form. So somebody asked, well, how do we know that there were an infinite number of particles? And the answer was that, of course, they didn't know that there were an infinite number of particles, but all particles that they were discovering were fitting in these straight lines. So it was reasonable to expect that the lines would continue forever. Okay? Of course, you will need higher and higher energies to produce those particles because they become more and more massive. So it was reasonable to expect that the contribution in the S channel to this scattering process of, say, 2 scalar particles would receive contributions from all these higher spin objects, okay? And we said, well, the interaction of two spin 0 guys with something that has spin j must necessarily involve j powers of momenta in order to contract these indices, okay? Since we have 2 of those vertices, they must contract among themselves, and we get something like this. So this is in the S channel. We said we had to have an infinite tower of states contributing in the S channel. There would also be the T channel to the same process. Okay. And we said that in field theory, the way we find something that satisfies this crossing symmetry is by just simply adding the 2 diagrams, right? Feynman told you that you are supposed to draw all diagrams that are possible. So you would draw this one, and you would also draw the one that looks like this. And probably you have done computations like that. Okay? Well, in order to be consistent with my conventions, this should be 3. So this would be the T channel. Well, this is the S channel. Okay? But having these infinite sums was a little bit strange, especially if you try to use them in loops. You will find that the theory will behave very badly, almost hopelessly badly. Okay? There will be no way to do anything with a theory that contains these higher spin objects. So Veneziano, or people at the time, came out with the idea that perhaps there was a way of relating these 2 channels and just writing a formula that will contain both things at the same time as different Lorentz expansions in different channels. Okay? So if you were interested in the S channel, you would take some master formula and you would expand in a Lorentz expansion in the S variable, or you would expand in the T variable and you would find one or the other. Okay? That such a formula exists is non-trivial, but it does. Veneziano found it, and here it is. Okay? So that's what we said yesterday. Now, what happens to this amplitude when you put it in loops? We have to understand what happens to this when the momenta grows very, very large. So when we take S to infinity and T to infinity, while these formulas individually will give you a disaster, the gamma functions somehow regulate the large momentum limit, and they give you something that depends on the scattering angle. So a nice function, which is finite, to the minus alpha s. So this thing decays exponentially. So this is almost hard to believe. I mean, it's so good. So this has a spectacular good behavior in the UV. Okay? So everything is looking great, so people were excited, and they tried to identify what kind of model would produce something like this as the scattering amplitude. Okay? Remember, this formula was found just by searching for something that would satisfy this dual hypothesis. And this is the object. So it didn't take long until people realized that you could get a formula like this. So you can get Veneziano, the Veneziano amplitude, from a model where what you are scattering are relativistic streams. Okay, so you have P1, P2, a relativistic string with momentum P1, one with P2, coming, interacting, and producing one with momentum P3 and one with momentum P4. Now, from the picture, you see why the dual hypothesis is satisfied for something like this. At least we can get an intuitive reason why this is true. If you look in the S channel, right, these two strings are coming, getting together, propagating for a while. Now, in the propagation, we can have a string that vibrates in any of the possible modes that the string can vibrate. Okay? There will be an infinite such modes, an infinite number of such modes. So that will give you this sum over all these possible spins. Okay? In the S channel. But you see that this picture looks pretty much the same. If you see it, well, again, it should be a 4, it should be a 3. If you see it in the T channel, so these two strings will come in. Well, remember, we're taking everybody to be incoming. So now it's even more symmetric. These two strings are coming in, propagating for a while, with an intermediate string here now, which can oscillate in any of the modes that it likes. So we have to sum over all of them, and it splits into the final two states. Okay? So you would say, well, everything is great. Okay? Now, surprisingly, in the 50s, we knew we had Maxwell, okay, which was a gauge theory with a gauge group U1. And note the following. At the time, people didn't see any other massless particles. There were no massless particles except for the photon observed in nature. So only the photon was observed in nature to be massless. But nevertheless, theoretical physicists sometimes study models just because they look interesting, and perhaps you can hope to learn something more general. So at the time, Young and Mills decided to extend this, and they found a model that has a gauge invariance of SU2. Okay? So that was very interesting. Well, perhaps not interesting for nature, right? Because if you have, as a gauge group SU2, how many gauge bosons do you have? 3. So you now got 3 massless particles, and you only see one in nature. So this is clearly wrong, right? So this Young-Mills theory is clearly wrong. Okay? But, well, it was, for theoretical interest, it was interesting to find a quantum field theory that could generalize this. Now, once they found this one, there was something else. They found, or people could find, gauge theories where you can have any number of gauge groups if you want. And you can have matter in many different representations. Do you remember what these things are? Everybody? Excellent. If you don't, go back and try to remember and review what these things are. Okay? These are the Young tableaux. They are useful to tell us what the representations are. So you can have matter fields. A given matter field can transform under different representations of all these groups, and you can have many of these things. So all these things together, they basically form an infinite number of families of theories. Okay? So they could have said at the time that they had discovered somehow a landscape of theories. Another reason to say that this certainly cannot possibly be anything that describes nature, right? Because if there was anything in nature, how could nature choose one of those, right? What would be the selection mechanism? It would be stupid that nature would choose something from here. So another reason why this thing is clearly wrong is because it has a landscape of theories. Very good. Well, but certainly this was very beautiful. But then people did more experiments, and they found that the behavior in experiments, when S and T grow very large, is only a power law decay.
Oh, sorry.
Yes.
I don't see the problem with landscape of theories.
Well, conceptually, people would say that if you could be very happy if this was the only consistent theory that you could make out of gauge theories.
Well, but for me, for example, there are different kinds of geometries in different kinds of spaces. But does that mean, well, so we have a landscape of theories, but is that a failure? I don't think
Well,
so.
I'm just saying what people could have said.
Okay, right.
I'm not saying what I would have said. So you would have said that that's okay. Somehow, this thing is providing a framework for describing gauge theories.
Right.
Okay. Excellent. So we have a power law decay experimentally, and that means that this thing is clearly wrong. Okay. Now this is wrong. This cannot possibly be what describes the strongly interacting particles because there is a power law decay. Well, what is a theory that replaces this theory as a theory of strong interactions? Well, it turns out, as we now know, of course, is QCD. Okay. And in the 70s, asymptotic freedom was understood, and now people understood why you can have Young-Mills theories, like SU3, which will have 8 terrible massless particles floating around, which we don't see, right? And confine them so that we don't see them at low energies. So in the infrared, we only see massive particles. Or in other words, at low energies, we only see massive particles, while the theory at high energies, in the UV, we have an SU3 Young-Mills theory. Okay? So I find it remarkable that something that just came out of curiosity ended up having a place, not only a place, actually the only thing that we know in nature precisely is just made out of Young-Mills theories, right? The standard model. Very good. Okay. So that means that this theory was almost, well, it was dead as a theory of strongly interacting particles. But already, when people didn't know this and people were studying string theory as a theory of strongly interacting particles, there was something else that was happening. Okay? So another, as people would say, another nail in the coffin of a string theory is that any string theory that people studied, when they tried to quantize it, it would do something very annoying, which is that classically, you wouldn't see massless particles, but of high spin. But when you quantize it, somehow, there would always be a massless particle of helicity plus minus 2. Okay? So that would be a massless particle. Of course, we don't see massless particles in the strong interactions. So this was a massless particle sitting there at the beginning of the spectrum. So you had lots of things that were massive. They were behaving like strongly interacting particles. But there was also this annoying object there. So of course, people tried to kill it as much as they could. So people tried to find symmetries that would prevent this thing from being created, anything they could. And they didn't succeed. So this guy could not be killed. Okay? They tried to modify the theory, adding different things, anything that they could do to the theory, and the theory resisted, and it was always there. So this was another reason why it was clear from the beginning that the theory would have troubles describing the strong interactions. So in 1974, after it was clear that this theory was going to be the correct theory of strong interactions, in 1974, Green and Schwarz decided to say, well, if we cannot get rid of this state, let's say that the theory actually predicts that such a state must be there, right? Because if you cannot get rid of it, it's a feature of the theory. But we know what that thing has to be. So in 1974, can be said that is the birth of a string theory as a theory of quantum gravity, or at least a proposal to be a theory of quantum gravity. Okay? Because this object was there, and there was no way to get rid of it. And since it didn't work for the strong interactions, we had to find another use for the theory. And why not? Let's give it a shot and see whether it's a theory of quantum gravity. Okay? Yes?
Has anybody proved that we cannot get rid of this felicity particle?
Well, people have studied, I think people believe that they have found all possible physical string theories, okay? And it's always there. You can find sort of unphysical string theories or topological string theories where the theory is topological, so it has different spectra and so on. But physical string theories.
But if you have a theory only of open strings, you wouldn't have that is equal to particles, right?
Well, the question here is, if you have only a theory of open strings, so somehow you know that this state is supposed to be a state of a closed string. So if you only have open strings, you would say that you don't have this state. But guess what? If you have two open strings, right? You have two open strings that come and interact, okay? At some point, they can close and produce a closed string, okay? So there is no way not to produce it. All right, very good. So the purpose of this course is to study string theory as a theory of quantum gravity, okay? So now we can really start the course. So this was the end of the introduction, okay? So if you didn't understand something at the up to this point, that's okay, because that was the introduction. Now we're starting the course. So in order to start the course, I figured that a nice way to introduce a string is actually to do it through general relativity, because you know general relativity very well, and you have taken several courses, and you also have taken quantum field theory. So I thought it would be nice to, or the intention is to start with something that you find familiar. Okay? So we are going to do something that sounds a little bit at first as if it had nothing to do with the string theory or anything that you know that should be related to string theory from the things you have read before. But let's do it nevertheless. So let's study GR in m dimensions. Plus scalar fields plus a cosmological constant. Okay? So we want to write down the action for this theory. Let's write it down. Now, what are the properties of this action? It's invariant under what kind of things? Well, the first one you know very well is that it's diffeomorphism invariant, right? That's a big deal about writing something that has GR in it, is that of course we know very well that this is not a symmetry, strictly speaking. It's an invariance, it's a redundancy of the description, right? So it means that the metric, the description using the metric has a redundancy. But this action has a global symmetry. Actually has a symmetry. We shouldn't even call it global, but people like to call it global. It's just a symmetry, really. That does something on the scalar field. What does it do? How can I transform the scalar fields so that this action remains invariant? Just the scalar fields, nothing else.
Real or complex scalar fields?
What can you do?
Are they real or yeah, they're real?
Real.
Add a constant.
Excellent, yeah. Only the derivatives enter, right? So why not add a constant? Okay, so we have this global symmetry. That's very good. Now this theory looks a little bit boring. Perhaps we can do something more interesting and make it a little bit more complicated in order to add more global symmetries. Okay? So what I want to do now is to replace this thing here and introduce many scalar fields. Okay, let's introduce many scalar fields. So I know I'm not supposed to do this, but I'll do it nevertheless. I'll just erase this and write it there. So I'm going to introduce many scalar fields. Okay. A linear combination of products of many scalar fields. Okay. Very good. Well, if my object here doesn't depend on phi, okay, so I'm assuming that this doesn't depend on phi, so this is just a matrix of numbers. It's not a function of phi. It's just a matrix of numbers. Then the global symmetry that I had before is still there. Well, not quite. There is something wrong in this formula. No, there is nothing wrong. Okay, very good. So I can do that. Is there any other global symmetry now?
Rotations.
Well, rotations, that would be rotations if M was the identity, right? But I guess what you're saying is that if I transform the scalars by any matrix such that this is satisfied, then this is a global symmetry of my action, right? That's very good. So since you were jumping ahead, maybe we can ask, what would that be if we choose M to be the identity? And we should also tell how many. Let's say we have I runs from 1 to D. Okay. So M is a D by D matrix. And if M is the identity matrix, then our global symmetry will be SOD. Can you think of another matrix that would be interesting? Yes.
Isn't it enough to be M to be diagonal?
For what? For having
SOD?
No. Very good. So now let's try something else. Let's try something that is -1 here. here zeros here, and here the identity d minus 1 cross d minus 1. Okay? So now you can tell me what's the global symmetry group in this way. SO1 comma d minus 1. Okay? Now, isn't that interesting? If you combine that together with this, so what does this look like? Looks like what?
Translation.
Translations. So you have translations, and the Lorentz group together, they form the Poincaré group. Okay? So it's as if people usually talk about the space where the phi can take values as the internal space, okay, of your theory, because we usually think that this is describing your theory in the space where you live. So these indexes are telling you about the internal space. But somehow, if we choose this M to do this, and we choose not to write something that depends on phi explicitly, only derivatives, we have something where the internal space looks like Minkowski space. So it looks like a nice Minkowski space. Now, the reason we don't do this very often in quantum field theory, well, there is a very important reason why we usually take this and not this in quantum field theory. Can anyone tell me?
We want the energy to be positive?
Yeah, it has to do with that, definitely. So if we use this one, what's going to be wrong in the action?
We have a negative or negative mass charge.
Right, one of the fields will have the wrong sign for their kinetic term. So we will be in trouble. Okay, so we don't usually do that because of that reason. But okay, I mean, we're just writing. We're just having fun at the moment. Okay, having done this, let's explore what happens in different dimensions. So let's consider. Oh, no, even before we do that, let's keep playing with this action. Let's write the equations of motion when we vary the metric. That's something you should also be experts, right? I mean, like, you probably have done it hundreds of times by now. So let's write the equations of motion for the metric. Okay, so we look at this action. So it's clearly the Einstein tensor. Okay, the cosmological constant contributes here. I just chose to put it here. Doesn't really matter. It could be on the other side. And on this side, what do I have? The energy momentum tensor of the matter theory, right? And what is the energy momentum tensor of this theory? That's something that you probably have done too. Have you done that? If you haven't, I encourage you to go ahead and compute it, okay? So compute the energy momentum tensor of this theory, and you should find something that looks like this. In fact, yeah, do it with this theory here, with the M and everything. So you should be able to find something that looks like this, Mij. So the ij indexes will have to be contracted somehow, okay? So the metric, this M should appear here in front. We need something that depends on these indices. So this is almost the only combination we can write down. But there is another combination we can also write down, okay? Which is something that depends on the metric, okay? Where these two indices come from the metric. But now we need something that contracts these two indices, but the only things we have are things like this, but we cannot make them depend on to have explicit indices. So we have to contract those. Okay. So that's the energy momentum tensor. Okay, so I encourage you to compute it again. Well, I mean, if you haven't done it, I encourage you to compute it for the first time. But if you have done it, please review it. All right, so now consider the case m is equal to 1. Why not? We should start somewhere. So let's do the case when you have only one dimension. Well, if you have only one dimension, your space only has time. Okay? So why not call x0 tau? Okay? So what I have as x there, I'm going to call it tau. I want to consider the case where my matrix M is actually the Minkowski metric. And since we're all familiar with these indices, let me just replace this by this, okay? Mu nu. Now my scalar fields, of course, cannot keep this index I. They should carry an index mu and nu, because these are the new indices, or the new notation for my metrics. So if I'm going to use these indices, and I'm going to think about this as a physical Minkowski space somehow, why not replace this notation by this more appropriate notation? Okay. Now, what happens to the metric? Well, the metric has only one degree of freedom, so it's convenient to define it. Since it's only the time component, the time component that appears, it's convenient to define it as something positive with a minus sign. Okay, it's just convenient. Okay. Very good. So let's write the action in this convention. Sorry. Yes, this is square. The minus it's outside, so it's minus e squared. So let's write down what the action is. So this is now an action for my new field E, and my field's X. Yes.
Why can we state that it's 1?
Well, because it's not. Of course. I think you're jumping ahead because you're saying, well, if you have diffeomorphisms invariant, right? Diffeomorphisms invariant, in this case, will buy you one function degree of freedom, so you can eat up one function from your action. Why not choose it to be the action, the metric, and choose it to be constant? Is that what you're saying? Well, that would be exactly correct. So since we have diffeomorphism invariant, okay, we can choose to use it to fix one function to be anything we like, and we can choose this function to be 1 if we want. Okay.
But here E is a function, it's not a constant.
Yeah, this is a function. Yes. Yeah, this is a field. It's a field, and X is a field. Okay, both are fields. So S is a function of E and X. Many X's, right? Okay, so let's write down the action. Well, the first thing to notice is that, of course, there is no Riemann tensor in one dimension. In fact, you probably have seen how many degrees of freedom are there in the Riemann tensor, right, in any number of dimensions. Well, if you haven't, you can work it out, and once we finish this, you can tell me what it is. So just use the symmetry properties of the Riemann tensor and then find out how many dependent elements are there. But in any case, in this case, the first term is absent, so we write d tau. Square root of minus g happens to be e. Then we have minus a half. Now we have g inverse. Remember that g mn with the scalar fields is actually g inverse. So we have 1 over minus e squared. I'm not going to write del tau xi, right? That would take too long. I'll write it just once, just in order to define this to be this notation, right? Derivative with respect to tau, which is the only variable we have, I'm just going to denote it as x dot. So here what we have x dot mu, x dot mu, eta mu. Okay, I'm translating everything that I have. Minus lambda. Okay? Very good. So let's clean this up a little bit. So what do we get? We get 1/2. Let's put the half outside. Okay, so we get d tau. This would be 1/e, x mu, eta mu, minus, I'll get 2e lambda. Okay? Well, now I want to compute the equations of motion for the field E. I could just do it using the energy momentum tensor that I got here because I know that R vanishes here. But let's do it directly here. Okay? You could just plug everything that we said here in these formulas, and you will get the same answer. But since this is so easy, we can just do it. We just want to find the equations of motion with respect to E, to the field E. So we find minus e to the minus 2 minus 2 lambda equals to 0. Okay? Very good. Now since this field doesn't have even a kinetic term, right? This field E doesn't have a kinetic term. Every time you see something like that anywhere, you should integrate it out. Okay? So integrating out means we find the equations of motion, we solve for the object, and we plug it back into the action and see what we get. Okay? So from here, what do we have? Well, we find that E squared is equal to what do we get? We get something like 2 lambda over. We should introduce a notation for this, right? This looks too big. Let's call it x squared, x dot squared. Okay? Let's just do that. So we get minus 2 x dot squared. Is that correct? Sorry. No, what am I saying? That would be for this. This would actually be the inverse. Okay? Now let's plug this in here. Okay? So let's use that E is square root of minus x dot squared over square root of 2 lambda. Let's use this in the action. So to write our effective action, so this is now our effective action for just x. So we get 1/2 integral d tau. When we plug this in here, we get something that looks like square root of 2 lambda square root of minus x dot squared minus, from here we get the same contribution, so what do I get? This is do I get to 0?
You need to have a minus one. The first one.
Sorry?
Equals to minus from e squared.
From e squared. What is the e squared? Oh, from where?
You are dividing status squared with minus square root of x status squared. So we need to add a minus sign. The first term.
Yeah. Oh, in the first term I have a minus sign. Excellent. So you have the same thing here. Thank you. It would be a little bit boring if I had 0. So what we get, so we get a factor of 2, so that cancels this factor of 2, and there is an overall minus sign, and we get something that looks like this. All right. So you probably have seen that before. Have you seen that action? Has anyone seen that action? Well, maybe.
Did you drop your lambdas?
Is what?
Did you drop your lambdas?
Oh, the lambdas. Oh, thank you very much. Yes. That's why you haven't seen it.
Yeah.
Well, maybe let's work a little bit more before I ask you if you have seen that. First of all, let's take the non-relativistic limit. Okay. So what is my x dot square? Well, if I'm really thinking about these x's as living in some space-time, so what I have here is something that looks like and if you will. So let's see, what do we want to do? Well, remember our metric is mostly pluses. Okay. So what we have is something that looks like minus d t over tau plus dx squared over d tau. Okay.
Squared.
Sorry. Squares. Well, we can put a square here. Okay? So in the non-relativistic limit, we can end up writing this as our action will end up being something that looks like 2 square root of lambda d tau times square root, taking into account the minus sign that I have over there. I can pull this out and make a change of variables so that this will turn into a t. Okay, this will be 1 minus dx over dt squared. And in the non-relativistic limit, this thing goes like 1 minus a half dx over dt plus higher order corrections. Okay? And now this action looks like dt. Well, there is a boring piece, right?
I think you should keep the power.
I should keep what?
Power of
dx by dt.
Yeah, sorry. Okay. Okay. Now, forgetting about this boring piece, what does this look like? It's the action of a particle. It's the kinetic term of a particle. Okay. If we interpret square root of 2 lambda as the mass squared of the particle. Sorry, as the mass of the particle. Okay, very good. See, you're all awake. Excellent. So now I can go back and ask the question. So let's plug that in here. If this is the mass of the particle, let's put it here. And now I can ask you, have you seen this before? You probably have in GR, right? Well, at the moment, it even looks a little bit boring, right? Because this is a particle propagating. This is describing the action of a particle propagating in flat space-time. So why don't we make it more interesting? So we could make it more interesting by replacing the metric by some general metric, okay? So if we replace by some more general metric that now depend on x, where x is the field here, okay? What we will get inside here is nothing but the action for a particle moving in a curved spacetime. Okay?
We can't see that.
Oh, yeah. It's a small problem in the design. Okay, very good. So what we have is our world line, tau, and our x's are mapping our world line into a space-time and the action is described by this object that you know very well. So the equations of motions for x would be what? The geodesic equations of motion of a particle in this curved space-time with the metric g mu. All right. Very good. But is there any advantage? I mean, this is the action that you usually write, right? Is there any advantage of writing the action in the way we did it here? So in other words, is there anything good about writing the action with E? The action we have over there. Let's actually replace this by what we know it is, okay? It's m squared. So is there anything good about writing the action in this form? It sounds like it was a waste of time, right? So we did all this just to land on the action that we knew. Is there anything good about this?
The equations of motion are linear.
Sorry?
The equations of motion are linear.
That's something good, but is there something else that is good?
Get rid of the square root.
That's true. Well, something else that is good. Wow, this thing is it's actually doing.
We can take the limit of massive herself.
That's what I was thinking. That you see, in that action, if you want to describe a massless particle, you will be in trouble. If you write down, if you start with this action, and you take m to 0, you will be in trouble. So in order to describe a massless particle, you better use this action. Here, m is just a parameter. You can take it to be 0 and nothing terrible will happen. Okay? Very good. But then we said that, or at the beginning, we said that we have diffeos in this action, diffeomorphism invariance. Now, in this case, it's just invariance under sending tau to be a general function of tau. So that's one function worth of degrees of freedom that we can eat up with this redundancy. And what better thing to choose than killing E or setting E to something, okay? So we can use this to gauge fix E to be 1. Okay? However, we cannot just gauge fix E to be 1 and forget about it in the action and pretend that it never existed, because in order to preserve this constraint in time, we have to impose equations of motion, which we wrote out here. So this has to be imposed as a constraint. So the equations of motion, we can gauge fix E equal to 1 as long as we keep its equations of motion. And the equations of motion were giving us x dot square minus what we know now is the mass square is equal to 0. Okay? So this should be imposed as a constraint. But just look at the action and ask, well, what's the momentum conjugate to this variable, to x? That is what we should call the momentum, right? But just by varying the Lagrangian with respect to x dot mu, we should get p mu, but that thing is nothing but x dot mu. So when we use this definition in here, we find that the momentum square of the particle plus m squared must be equal to 0. But that's precisely the dispersion relation that we should get for a free particle with mass m squared. So this looks very good. So we should keep in mind that this is a constraint that has to be imposed. You probably haven't seen this exactly like this in GR, because in GR people usually choose a different convention. So there is a GR convention. Which is to choose E to be 1 over m, I think. So if you choose E to be 1 over m, what happens to the constraint? What do we get? We get something that looks like minus, this is what we get, minus m squared, x dot squared minus m squared equal to 0. And therefore, we get that x dot squared plus 1 is equal to 0. And this is probably what you have seen in GR, right? That you should impose this constraint. Okay, very good. So I think we have beaten to death the case m equals 1. Okay? Nothing new, I hope. You probably have seen everything we have done now. So let's do something new. Let's start with n equals 2. Or you can do m equals 2 as an exercise. Well, so that when you do the exercise, we all get the same notation. I'm just going to, we have time to just to establish the notation of translating our general field theory to the case m equals 2. So now consider m equals 2. Okay. So we now have two coordinates, x0 and x1. People like to call these coordinates tau and sigma. So we're going to use that notation. So in our master action over there on the top, m is equal to 2. We have two coordinates, one space and one time, and we're going to call them tau and sigma. Okay? Our scalar fields will still be x mu's of tau and sigma, because we will still take our matrix M to be eta mu. Okay? Very good. So now we can benefit from all the work we did there, because we can almost sail through this case just by translating everything we have over there. But before we do that, since I want to study the equations of motion, I want to see what the Riemann tensor is in this case. Okay? So I hope you had time to find out how many independent components of the Riemann tensor there are in m dimensions. Have you done that counting before? So that's important. That's what's important. I mean, that you don't remember what it is, that's not that important. Is this starting to sound familiar? 112? Remember, the way you get this is by saying, well, if you define this guy, then you can prove that this object is antisymmetric under the exchange of these two indices, is antisymmetric under the exchange of the last two indices, is invariant under the exchange of these indices. This pair goes here and this pair goes here. And if you fix one index and you cyclically rotate the remaining ones, you get 0. From these symmetries, you can conclude that the number of degrees of freedom, independent degrees of freedom, will be that, while naively you would have thought that it was n to the 4th. Okay? Good thing is much less than that. Well, all this is just to say that in our case, m equals 2, what do we get? So the number of degrees of freedom is 4 times 3, 12 divided by 12 is 1. Okay? So our Riemann tensor only depends on one parameter. There is only one degree of freedom. Okay? So that's good because if we can write down anything that has the correct symmetry properties, the proportionality constant, or the proportionality, will be our degree of freedom. It can be nothing else, right? So we can immediately find out what this is by just writing something. And the only thing we have at our disposal is the metric, right? Which, in fact, I forgot to say that in this case is convenient. Or people like to call the metric in this space, people like to call it H, okay? And since we're in our case n equals 2, we should really do something like this, mn pq. So we have to write something in terms of the metric that has the correct symmetry properties. If we find one such thing, we are done. Because the only degree of freedom will be something that multiplies whatever we find. Well, we need something that is antisymmetric in these two indices, and is invariant under the exchange of these two. Well, it certainly has to have 2 powers of g. It should be antisymmetric somehow. So it should be something like this. 2 powers because we need 4 indices. So we can have something that looks like this, say, and then make something antisymmetric in these 2 indices, and then it will be antisymmetric in the other 2 automatically. So we do PQ, QP. Now you can check that this is also invariant under the exchange of this pair and this pair, you get exactly the same object. Okay? Very good. So this alpha is our degree of freedom. Let's find out what that alpha is. Okay? In terms of the only other, this alpha must be a scalar, right? Because it doesn't have any indices. And what's the only scalar that we have in this theory? The Ricci scalar. So this thing must be proportional to the Ricci scalar. So let's try to find out what the constant of proportionality is. So how can we do it? Well, let's try to produce the Ricci scalar on this side, and then we will get that. So first we have to produce the Ricci tensor, and that we do by contracting this index and this index, right? So that will give us R and Q. So once we do that, what do we get here? We get alpha. We get this guy with this guy. That gives us, in 2 dimensions, it gives us a factor of 2. Minus. Now we contract this with this. It's just contracting 2 indices here. Or you can think about that as this making a delta function out of this, which changes the index here. So we just get GQN. So we get alpha GQN. Finally, R is G and Q, R and Q, which we take from this formula, and then we get 2 times alpha. Therefore, alpha is R half. Okay? So that's good. We haven't solved any differential equations, and we found what alpha is. So we can just put it here. Actually, instead of putting it here, it would be more useful to put it here. Yes?
Don't we get a factor of m for dimensioning R?
Yes, indeed. But m is equal to 2.
Oh, right.
Now you're precisely right. But we're only doing it in m equals 2. Right. Remember, we're using that this thing has only 1 degree of freedom.
Yeah.
Otherwise, this would be incredibly complicated. Right? Very good. So we're almost, let's move this up. We're almost done to finally use our blackboard over there. All our hard work. Let's use our formula there. What do we find? Well, we find a surprise. The Einstein tensor vanishes, right? So we found from here that in 2 dimensions, is equal to 0. The Einstein tensor is equal to 0. So when we find the equations of motions are telling us that lambda must be equal to T and n, to the energy momentum tensor. But we also know what the energy momentum tensor is. Let's now translate the energy momentum tensor in our notation for n equals 2. So it would be what? It would be eta mu nu del n, okay, x mu del n x nu minus a half h mn h pq del p x mu q x nu. Okay? Very good. So this is it. But just out of curiosity, let's compute the trace of this object. In other words, let's contract it with the metric to compute the trace. What do you get? Zero. here, we get 0. So this is a traceless energy momentum tensor. Well, let's look here. So let's compute the trace here. Well, by computing the trace there, we find that lambda must be 0. So the only cosmological constant that is consistent with equations of motion is actually lambda equals to 0. Okay? Very good. So we now have this. We can now go back to our action and ask again, why are we getting that the Einstein tensor is equal to 0? What happens to gravity? Right? What happened? We have a kinetic term. We have this action. Remember, I'm translating from that formula to the notation we have here. We have this object there. We know that the Ricci scalar is not 0, right? We didn't find that it was 0. And yet, this action doesn't give us any equations of motion that are interesting. How come? Sorry? Probably this expression is a constant, and that's true. So it turns out that in 2 dimensions, this object is a number. And it's not only a number, but it's a number that tells you about the topology of the space where this thing is being integrated over. So if we make this Euclidean, okay, by sending tau to I tau, and we think about this as an Euclidean object, meaning a Riemann surface, or a closed surface, we can integrate this action over anything we like. It could be over a sphere. Okay, if we make this Euclidean, we're happy to integrate this over a sphere, or we're happy to integrate it over a torus, or anything we like. And this number here, or this object, computes for you the Euler number of your spacetime, of your 2-dimensional spacetime. Well, if you make it Euclidean, it wouldn't be a spacetime, but that would be the computation that you get from here. So that's just a number. So we don't see it in the action, really. It's not doing anything. So we can conclude today by just writing the action we get in the end. Okay? So if this is a number, we don't worry about it, at least for the moment, and simply write what we get. Let's actually write it here. So we have an action for our metric and our fields, which is nothing but the integral. Sometimes people like to call tau sigma 0 and sigma 1. The reason it's convenient is that I can write d2 sigma here. I get -1/2 square root of minus h -1/2 hmn del m x mu del n x mu times and this action is the famous Polyakov action. Okay? So tomorrow, and I encourage you to do it today, try to do everything we did for the 1-dimensional case for m equals 1. Try to repeat it for this action. Okay? So what would be the first thing you should do? Integrate out h to see what action you get. What would be the analog of this thing? Find the analog of that action. Okay? Remember, we got it by integrating out E in this case, you should integrate out h by using the equations of motion. Okay? Then go back to the action, even to this action, go back to this action, and try to study more carefully all the symmetries of this action, or all the invariances of this action. This particular guy, given the fact that the energy momentum tensor vanishes, has an extra invariance that the general one didn't have. Okay? So there is another invariance on top of the diffeomorphisms that this action has. So your job is to find what it is. Okay? Find the new invariance and find the action you get by integrating out the field H. Okay? So yeah, we will do it tomorrow, but you should do it today.